Hello and welcome to my presentation. I am Mohammad Reza Fanisani, and in this presentation I will explain how by using model simulation and edit distance measure we can approximate the conformance value faster. The other authors of this paper are Juan Gonzalez, Sebastian Vanzels, and Will van der Aalst. We are doing research in process and data science chair of RWTS University of Aachen, and our main focus is process mining. Conformance checking is one of the main subfields of process mining. By conformance checking, we aim to detect how real event data are deviated from the designed or sometimes discovered process models. For doing conformance checking, we usually assume that we have a process model and an event log. There are different ways to show a process model. Here, in this slide, we use the Petri net notation to show a process model that could be a bit complex for end users to interpret it. In this slide, you also can see an event log with 20 traces. It contains 5 unique trace variants that the most frequent one has 10 traces. There has been some different techniques to compute the conformance checking, for example, using footprint and token-based replay. However, nowadays in both academia and in industry, we use alignment techniques for conformance checking mostly. Unfortunately, computing conformance checking using alignment is very slow and sometimes inapplicable for big real event logs using normal hardware. There have been some approximation techniques provided to improve the performance of alignment. However, sometimes the improvement is not high, and sometimes we couldn't provide a guarantee for the actual approximation value. It should mention that some of the approximation methods are slower than normal alignment technique. The outline of the remaining part of my presentation is as follows. First, I will explain how we can compute the alignment using the edit distance measure. Afterward, I will explain our proposed method and somehow showing the experimental results. Finally, I will provide the conclusion with some possible future direction in this area. We can consider a process model as a set of traces that can be replayed by the model. Of course, if there is any loop in the process model, it produces an infinite set of traces. For example, here you can see the corresponding set of traces for the given Petri net. To compute alignment of each trace in the log with the model, we should first find the most similar trace in the model, the log trace, and afterward we compute how these two traces differ with each other. It is very important to consider that to find the most similar model trace and also to compute their distances, we can also use the adapted version of Levenshtein distance that we call it as edit distance. It simply measures what are the minimum number of insertion and deletions transfer one traces, log traces, to another traces that is the model trace. For example, suppose that we want to compute the alignment cost for trace like AE. The most similar model trace to AE is ABE, and we can transfer AE to ABE by inserting B between A and E. Therefore, the edit distance of them is 1. As I said, a process model could be seen as a set of traces. The point is, for real scenarios, this set could be very large and, of course, infinite, set, and consequently finding the most similar trace among them will be very time consuming. Therefore, we aim to consider somehow a subset of model behavior instead of the whole trace. So we call this subset MB. It is very important to note that when we use MB, that is a subset, instead of all possible model traces, we may provide a higher alignment cost because maybe the most similar model trace is not placed in the MB. However, the alignment cost that computed by MB is always an upper bound for the actual value. So one question is, how could we have this subset MB? How can we generate? There are two main methods. We can select some of the log traces and using the normal alignment technique to find the most similar traces for them. Or we can simply simulate the model and keep as much as traces that we like. In this research, we aim to simulate the model. However, we aim to simulate traces in the model that are closer to the event. To do that, we can use a prefix tree. We start from an empty sequence and expand a possible node somehow from the tree. We use the behavioral probabilities in the log, in the events log, to prioritize the node in the prefix tree. And after that, after selecting one node, we expand the node and add all the prefixes, the expanded prefixes to the prefix tree. We continue this simulation until there is no node for expansion or we simulate enough traces. The output of our simulation method is a fourth tuple. Simulated trace, the length of the shortest model trace, the length limit of prefix k, and all prefixes up to length k. In other words, we know that, for example, up to length k, we discovered all the prefixes. We generate so all the prefixes up to length k. Note that our proposed approximation approach is completely independent from the simulation method. Therefore, any other simulation technique could be replaced by this simulation method. Also, please note that if an alternative simulation technique couldn't provide or guarantee k and pk, we are able to replace k with 0 and empty set instead of k. So the approximation method could work with this value. And now I want to explain how by using this simulation we can provide approximation and also bounds for the alignment cost. As I mentioned before, by using a subset of model traces instead of the whole model and the edit distance measure, we will provide an upper bound for the alignment cost. For the lower bound, we return the maximum value of 3 possible lower bounds. You can see them by green here. First, we compare the length of the log trace by its projection on the model activity. For example, if the log trace have activity Q that is not presented in the process model, we need at least one deletion. Because Q is not in the model, we know that we should. Another lower bound is computed by comparing the length of projected log trace and the length of the shortest trace in the model. If the projected log is shorter, it is clear that we need at least some insertion to have a trace with length of the shortest path in the model. The last lower bound is corresponding to comparison of prefix log trace up to k, that is pk, and the set of all prefixes of the model up to length k. as we have the set of all prefixes up to k, to convert our log trace to one of the model traces, we should also convert the prefix of the trace. So if we want to convert a log trace to a model trace, we should also convert the prefix one. So we use the subset of prefixes up to k to somehow guarantee the lower bound. To approximate the alignment cost, we remove the repetitive patterns of log traces and compare them with the simulated log. Note that the approximated value should be always between lower bound and upper bound. In this, somehow in the paper, we somehow formally showing how we compute the bounds and also the approximation. So please, if you want to know the exact way of computing bounds, please refer to the paper. Here, you can see using our method, we are able to approximate the conformance value for example event log and the given process model. Suppose that we, using our simulation method, we expand the process tree as presented in this figure. So we will have the simulated log only one trace, that is ABE. The shortest path in the model, MS, is 3. Also, when we discover all prefixes up to length 2, A is equal to 2, so we have empty sequence, prefix A, AB, and AC. So, for example, for trace AE, that is the second trace, the most similar trace is ABE. So the cost is 1. That is the upper bound for the alignment cost. The lower bound, we know that the length of this trace is less than 3. And we need at least one insertion. So because the upper bound and lower bound are the same value, we know the exact. To evaluate the proposed method, we implement the approximation method in both Chrome and RapidProm platforms and apply it on 7 real event logs. Some of the event logs are big and some others, like sepsis, have several unique values. For process models, we discover process model using inductive binder with 4 different noise thresholds. We use the sampling method with 10% of variance. So we select 10% of most frequent variance and using alignment behavior to generate MB. And when we generate MB, we consider the same amount for simulating traces for our approach. Here you can see how, by using approximation method, we are able to improve the performance of conformance checking. You can see in most of the cases, the PI value, that is the performance improvement. You can see the formula in the left side. The performance improvement is higher for our approach. However, the bandwidth for the sampling method is tighter compared to the simulation method because we really computing alignment for 10% of value. For example, for the log BPI challenge 2019 and using inductive binder 0.2, we provide an alignment value more faster, somehow 10 times, 1,000 times faster, and approximation error is just 0.004, different from the actual value. For the road traffic fine log, we are also super accurate. In this slide, we aim to show how by increasing the number of simulated event log, we are able to reduce the bandwidth. However, it also reduces the performance improvement of this method. For example, for BPI Challenge 2018 event log, By increasing this simulated log from 10 to 1000, the performance improvement is reduced from 16 to 8. Note that for the IRTFM event log, we are not able to generate 1000 traces. That's the reason we don't see any difference in the values. In this slide, we compare our simulation method that uses the event log probabilities, behavioral in the event log, with a random simulation method that generate traces without considering the event log. We see that, as we expected, that random simulation is faster. However, our method is provide more accurate bounds and approximation. So in general, in this slide, we can see how by increasing the somehow the size of simulated log, we somehow also again have less performance improvement. To conclude, we propose an approximation method using a guided simulation and a distance metric for conformance checking. The proposed method is able to provide bounds for the approximation fitness value and also show deviation rates of activity. I don't cover deviation of activity in the presentation. A very good advantage of our proposed method is that it is dependent from the simulation method and also the process model notation. So we can also apply this method for BPMN model or fuzzy graph, or even the cases that we don't have any process models. I see in some commercial tools, you can do conformance checking by selecting some of the variants in the log that we are completely sure that they should be part of the model. So in the background, they discover a model using normally inductive minor and apply the normal alignment technique. However, using this approach, we could directly apply conformance checking with the selected variant. So we consider the model as the selected variant. And in my view, it's super practical. To extend this work, we aim to provide an incremental conformance checking that incrementally increase the size of simulated log and let user start the incremental process when the bandwidth. Moreover, we aim to provide provided somehow bounds tighter and also computing deviation for activity that makes our approximation more useful for the diagnostic purpose. My presentation is finished. I want to thank you again for your attention. Please feel free to contact me if you have any question or if you want to discuss more about this research. Take care and stay safe.